Hey everybody, Mrs. KJ here, going over 6.06, dry cells. Dry cells and batteries generate electricity for our everyday use. Think of things you use that need batteries. Flashlights, wristwatches, and calculators are disposable batteries. Cell phones, MP3 players, and laptop computers use rechargeable ones. Batteries are voltaic cells that combine the half cells into one compact unit. In this lesson, you will examine the chemistry of dry cells and batteries and compare it with the chemistry of voltaic cells. Goals for this lesson: compare and contrast a dry cell with a voltaic cell. Describe the chemistry of various kinds of batteries. So we have a dry cell. A dry cell can have a zinc casing where the anode is oxidized. A dry cell can have a carbon rod, the cathode that conducts electricity, and the dry cell has an electrolytic paste where reduction reaction occurs. So these are all the parts of a dry cell. Again, here's the study guide, and let's check it out because there's a lot of vocab words. Anode, a negative terminal of an electrochemical device. Battery, a series of metal plates or voltaic cells and separators which produce a flow of electrons. Cathode, the positive terminal of an electrochemical device. Dry cell, a device that produces electricity by containing both half reactions of a redox reaction in a single unit. Voltaic cell, an electrochemical device that produces electricity from chemical reactions. Dry cells are voltaic cells used in many common items. Voltaic cells are electrochemical cells that convert chemical energy into electrical energy. Voltaic cells use metal strips as electrodes. The strips are either in the same solution or in separate solutions that are connected often by a salt bridge. So like the pictures that we saw in previous lessons where they're in beakers. Oxidation reduction half reactions occur at each electrode. There are pathways for the flow of electrons, so for example a wire connecting the electrodes. Ions flow through the solution to maintain neutrality, so that's what the salt bridge is for. A simple type of compact voltaic cell called a dry cell is used in many devices such as flashlights, cell phones, and MP3 players. A dry cell and a battery are not the same thing. Even though in real life we call them batteries all the time, chemically that's not the correct definition. What you put in a flashlight is properly called a dry cell. So we have AA dry cells, AAA dry cells, D dry cells. Okay, even though we call them all batteries, they're technically dry cells. How does a voltaic cell work? All right, so this is our voltaic cell again. As you can remember, we have the two beakers separated by the salt bridge. The electrons go up and they can light up a light bulb, or in this case, it's just sensed by the voltmeter, and down here. All right. So a zinc copper sulfate voltaic cell operates like this. Zinc is oxidized at the anode. So solid zinc with a 0 charge turns into zinc plus 2. So it lost the electrons. Woohoo! It's more positive. The electrons flow up the zinc strip through the wire. So those electrons got to go somewhere, and they go up the zinc strip. They go through the wire. They light up the light bulb or whatever you have hooked up here. They keep going all the way over to the copper side. Meanwhile, those zinc plus 2 ions move into the solution. Okay, so the electrons went up and the zinc plus 2 goes down here. And there's sulfate ions move from the other half cell through the salt bridge into the other half cell to balance the increase of the zinc plus 2 ions. Okay, so in other words, we have our zinc, the electrons went up, the zinc plus 2 went down. And if you notice, there's sulfate. Well, that sulfate originally came from over here. And the sulfate travels through the salt bridge over here, and they hook up together. And by hook up, I mean chemically bond. Electrons flow through the wire from anode to cathode because electrons are negative. They're attracted to positive, so they have to start at a negative end and go to the cathode. Copper plus 2 ions, okay, are reduced at the cathode. So now we're at the other side. So we have copper plus 2. It gained 2 electrons. Electrons are negative. Now the charge is 0, so the charge is lower. It was reduced. Elemental copper is produced. Electrons flow from the wire into the copper strip. So remember, the electrons are coming down, they meet up with the copper plus 2, and they form regular copper as a solid, and it hooks on here, which is why this is kind of like a circular shape. It's showing that it's growing. There's more and more copper ions coming out of solution and coming onto this piece of metal. Copper plus 2 ions move from the solution onto the strip, and the sulfate ions leave this half cell through the salt bridge to balance the decrease in copper plus 2 ions. Both half cells remain neutral. All right, so again, we already talked about that, how the sulfate goes up and around. And there's also sodium coming down on this side, which they kind of ignore, but it's there. Okay, now let's talk about a dry cell. So, voltaic cell, dry cell. A dry cell has the same working principle as a voltaic cell, but is arranged in a compact unit. A dry cell consists of the following parts: an outer steel casing, a zinc casing, which is the anode, cardboard separator. Now this piece of cardboard separates the half reaction and acts like the salt bridge of the voltaic cell. There is a paste composed of electrolytes, often manganese dioxide, with other alkaline compounds, and it replaces the solutions in a voltaic cell. So obviously there's not beakers of liquid, right, inside your MP3 player. Instead they have this paste. Then there's carbon, specifically in the form of graphite. So pure carbon can be diamonds. Pure carbon can be the stuff that you use to write with in a pencil that we call pencil lead. It's actually pencil graphite. So in this case, the pure carbon is graphite. And the cathode conducts the electrons. Typical dry cells have a paste of manganese dioxide, zinc chloride, ammonium chloride, and water. Alkaline dry cells, or what we call alkaline batteries in real life, have a paste of manganese dioxide and potassium hydroxide. Sorry, manganese dioxide. Yeah, I did say that right. All right, parts of a dry cell. So again, so here's the wire, right? We connect the bottom and the top of what we call batteries, but are really dry cells. So we have the positive terminal or end, and that's connected to the graphite rod. The paste is in the inside. That's where the reduction takes place. We have the negative terminal, and the solid zinc layer is the anode. As in any electrochemical cell, the reaction in a dry cell is a redox reaction. All voltaic cells, including dry cells, start with an oxidation reduction reaction. The voltaic cell used let me take a deep breath. The voltaic cell example used in a zinc-copper redox reaction. Most dry cells use a zinc-manganese dioxide reaction under alkaline conditions. The reduction reaction shown on screen may also be 2 molecules of manganese dioxide plus 2 NH4 plus 2 electrons yields. Now if you noticed here, we have Mn2O3 plus 2 NH3s plus water. In either case, here's the big idea: manganese is reduced. All right, so we have our oxidation here. We have zinc plus 2OH yields zinc oxide plus water plus 2 electrons. Okay, the balancing, they put this on here so you can see that, oh look, there was 2 negatives up here. Now those 2 negatives are split off, and that's where you get the 2 electrons from. The reduction, manganese plus 4 gets reduced to manganese plus 3. So 2 manganese dioxide plus water plus 2 electrons yields Mn2O3 plus 2 OH negative. All right, we know manganese has a charge of plus 2 because, do you guys remember back when we had to make chemical formulas? Okay, so if we look on the periodic table, oxygen is in group 6A. So it has how many valence electrons? It has 6 valence electrons. So how many more does it need? It needs to gain 2. So its charge is negative 2. Okay? And we don't know what manganese charge is. So I'm putting an X for an unknown like in algebra, because that's why we have these messy middle transition metals, because they can have multiple charges. All right, we know that our final answer here is MnO2. Okay, so you guys remember how we cross multiplied? Basically, the 2 goes down there, the x goes down there. And so originally you would think, oh, the Mn should have a charge of 2. But it doesn't. It has a charge of 1. So that tells us that it's been reduced. Okay, what if manganese had a charge of 2? What would that reduce into? Well, they would both reduce and it would just be MnO. But we want it to be MnO2, so that tells us that manganese had to have a charge of +4. All right, so if we reduce both of these now, we reduce the 2, reduce the 4, and that's how we get manganese dioxide. So just kind of a reminder of how they get that. All right, the basis for electrochemistry is the oxidation-reduction reaction. In a dry cell, the zinc casing is the anode. Zinc is oxidized. So we have solid zinc yields zinc +2 electrons. We know it was oxidized because the charge went up from a 0 to a +2. And now the zinc is aqueous. The zinc casing accumulates electrons and becomes negatively charged, and thus is the anode. When the positive and negative terminals of the dry cells are connected by wires, the electrons will move from the zinc casing into the negative terminal, or the cap, or the end, and out through the wire. So electrons move along the zinc layer into the negative terminal, and out the wire. Okay? Oxidation occurs at the anode in a dry cell. Reduction occurs at the cathode. The electrons, remember again, flow out of the negative terminal. Those electrons power devices such as flashlights. The electrons then continue down the wire and enter the positive terminal, or in this case they go around, and they enter the positive terminal of the dry cell. In a dry cell, the carbon graphite rod is the cathode. Carbon conducts electrons, but it is not reduced itself. Instead, the reduction reaction occurs when the electrons flow into the paste surrounding the cathode. So the electrons have to go back in this end, but then they go into the paste and they get reduced. Manganese dioxide within the paste gets reduced. So manganese +4 gets reduced into manganese +3, which is why we have a 3 there. And so that's happening in the paste. It's kind of like there's an extra step going on with inside your dry cells. Electrons flow out of the cathode and into the paste. A dry cell is a compact joining of 2 half-cell reactions. Zinc in the casing is oxidized. The casing is the anode. Electrons flow out of the negative terminal. Electrons pass through the wire and into whatever it is it's powering and back around into the graphite rod. Electrons exit the graphite rod and go into the paste. The graphite rod is the cathode, although it's the paste, the manganese dioxide within the paste, which gets reduced. All right, so I'm going to stop here. I kind of wanted to get through all this, and now I will add some stuff into our notes as far as dry cells. I added to our notes voltaic cells. Think of the 2 beakers connected by the salt bridge. Dry cells, think of what you call a AA battery. So parts of the dry cell. It's the outer steel container, the zinc casing or the anode, cardboard separator, it separates the half reactions and acts like the salt bridge in the voltaic cell, paste composed of electrolytes, often manganese dioxide gets reduced and replaces the solution in a voltaic cell, carbon graphite rod, the cathode that conducts electrons but itself is not reduced. So then we have the picture. A dry cell is a compact joining of 2 half-cell reactions. 1. Zinc in the casing is oxidized. The casing is the anode. 2. Electrons flow out of the negative terminal and power the device. 3. Electrons go into the graphite rod. 4. Electrons exit the graphite rod and go into the paste. The graphite rod is the cathode. 5. The manganese dioxide within the paste gets reduced. And I completed the picture so you can follow the electrons all the way around until they get reduced. All right, there is more to the lesson, and we'll finish that in the next video.